Good. If I see that it goes over quite a lot, then I'll combien dans le cours de quoi? Ok, quand même. Ouais. Mais c'est pas le concept. Ouais, mais ça m'a fait fantastique, ouais. C'est un nouveau postdoc qui est dans l'Institut CLA et qui travaille avec moi, mais aussi Laurence, Joseph Choi. Il vient tout juste d'arriver au Canada. Donc, son parcours, c'est qu'il a grandi en Corée du Sud. Il a fait son bac à l'Université de Yonsei. Puis ensuite, il est allé faire un doctorat aux États-Unis à University of Oklahoma pour travailler avec une chercheuse qui est très connue dans le domaine des trous noirs. Et des trous noirs qui accrètent beaucoup de matière, qu'on appelle des quasars. Elle s'appelle Karen Laley. Il a fait son doctorat vraiment sur ce type de trous noirs en particulier et les spectres qu'on obtient de ces trous noirs, qui sont très complexes à analyser. Puis pour ça, il a utilisé des techniques d'apprentissage automatique. Il est très, très, très impliqué dans tout ce qui est EDI. Donc, il a fait partie de beaucoup de comités durant son doctorat. À son université, mais aussi à l'échelle nationale aux États-Unis. Donc, très impliqué là-dessus et il continue à s'impliquer dans ce domaine-là à l'Université de Montréal. Pour son postdoc, si ça vous intéresse, il va continuer à travailler sur les trous noirs, de vraiment côté spectroscopique des trous noirs. Qu'est-ce qu'on obtient, qu'est-ce qu'on peut voir avec les spectres. Il va aussi joindre la collaboration qui s'appelle Learning the Universe, qui est une collaboration à laquelle l'Université de Montréal participe. Pour ceux qui ne savent pas, cette collaboration vise à faire les prochaines grosses simulations cosmologiques au niveau international qui vont remplacer Illustrious, qui était jusqu'à maintenant les plus grandes simulations cosmologiques. Donc, voilà, donc, ça me fait vraiment plaisir de l'accueillir. Puis, take it away.
Much for the introduction. I think I only understood like half of that, but I'm getting there. So today, and also want to thank you for giving me the opportunity to give a talk at the astronomy seminar. I want to also thank all of you and the Bill for attending today's talk. So today I'm going to be talking about quasars. So I'm an observational quasar astronomer, and I study particular quasar outflows by analyzing the spectra of broad approach line quasars. In particular, I use our group's spectrum analysis software called SimBAL, which I will describe a little bit more in detail in the later slides. So why am I interested in understanding quasar outflows and quasars in general, or why do astronomers want to study quasars? So one of the big picture ideas, a question that I like to pose is that astronomers want to know why the galaxies look the way they are. Okay, so wait the way they are. And this is a publicly filled image. May not be as exciting as a new data WST image, but what I want to show you here is that this optical to near infrared image, we see that the galaxies have various different morphology and shapes. some here in the red, blue and spiral arm, and some have red and fuzzy different shape. And astronomers have found out that the different shapes and different colors correspond to them having different properties such as age and their star formation history. And furthermore, the idea of galaxy evolution came about is the idea that with time, the galaxies evolved to have different shapes and different colors. And we're interested in understanding what's the physical mechanism behind this galaxy evolution. And some may study galaxy cluster like Julie, or some may study galaxy environment or galaxy interactions. But here I'm going to be talking more about the black holes and how I use the black hole astrophysics to understand this mechanism. So the black hole, most massive galaxies, most if not all of them, are known to have supermassive black holes in their centers. And for example, the supermassive black hole in the Milky Way there's a black hole with the mass of about 4 million solar masses. And in M87, there's a much massive black hole with about 6 billion solar masses. And what's different than the black hole in the Milky Way is that the one in M87, it also has accretion disk, here pictured EHT, and also a radio jet. So this image is taken with a spitzer, but you can also see in the spitzer image that there's a radio jet. So what makes this M87 black hole much special and different than one in the Milky Way is that with the structure, what they indicate is that this black hole is actually actively accreting, and this actively accreting black holes we call them active galactic nucleus, or an AGN. So why? So I said we want to study the galaxy evolution, and for that I want to study the supermassive black holes. But why? Why is that? So observational evidence seems to suggest there is very strong type correlation between the two properties. The property of the black hole, the plot here shows the y-axis, the black hole mass, and the x-axis is the mass of the central bulge. Or this relationship can also be called the M-sigma relationship. And this seems to suggest that the supermassive black hole and the host seem to co-evolve, and this co-evolution is the one that's driving this tight correlation between the two properties. So that's the observational evidence to suggest that there's something going on between them. And from the cosmological or theoretical point of view, in the cosmological simulations, for example, where they're trying to kind of create galaxies and trying to evolve them over time in their computer simulations, they found that they needed a special ingredient to make that happen, to make their simulations to actually create the realistic galaxy population that we see out in the universe. So that ingredient is called feedback. So what they find is that in order to successfully convert this blue star-forming spiral galaxy, or the blue star-forming galaxy, into a red quiescent or non-star-forming galaxy, there seems to be a process called, they call the feedbacks needed to make that happen. And this feedback is a mechanism, the way that central supermassive black hole imparts energy, mass, radiation, and heat to the host galaxy, and disrupting the physical conditions of the ISM host galaxy, or in some cases, to change the physical properties of the surrounding environment. So combining these two information, this seems to suggest that this feedback process is quite important, and this feedback process might be the one that can explain this co-evolution between the supermassive black hole and the host galaxy. So it seems like we've solved all the problems. However, the biggest mystery so far that we have is that we're just still not certain how what form the feedback takes. So in other words, we don't know how the central supermassive black holes communicate or influence this host galaxy. And they must communicate a lot in order for the supermassive black hole to totally change the evolutionary path of the host galaxy, for example. And in order to study this problem, to tackle this issue, I'm interested in looking at quasars. And quasars is one of the very attractive candidates to study this black hole feedback mechanism because, first of all, to briefly explain their characteristics, and if you have any questions while I'm explaining, please feel free to interrupt me and ask me questions for collective purposes and whatnot. So the quasars are one of the brightest galactic objects, and it's basically formed when a gas falls into the black hole, creating an AGN, basically. But quasars in particular, they have massive black holes, and on top of that, they have just tons of material falling into the accretion disk. So they're basically, so in other words, they're AGNs, but they're extremely luminous AGNs with a typical luminosity of 10 to the 45 Earths per second. And this enormous amount of gas that's falling into the accretion disk and creating the black hole they create sufficient and so powerful energy and the strong electromagnetic radiation that they often, in most cases, outshine the entire host galaxy. So if you compare the spectra of a low luminosity agent and the high luminous high accretion rate agent, you see in the luminous agent and quasar spectrum, you can barely find any signatures of the galaxy emission lines or galaxy continuum in the spectrum. And they accrete almost at the theoretical limit, or if not more, of roughly about, for a typical quasar, they accrete about tens of or up to hundreds of solar masses per year. And I found this so I found this video just to kind of give you an idea of what the quasars may look like, and more importantly, to kind of give you an idea of the different size scales. So, so this is imagining you have some sort of magical spacecraft, and you're like zooming into the central supermassive black hole. So first, now we're seeing is a galaxy. Roughly, the galaxy size scale is about a kiloparsec or 10 to kiloparsec size scale. Then we're gonna zoom into the central region to see the AGN structure, and you will see a dust obscuration structure called torus, and also you can see the accretion disk and central black hole. So zooming into these this quasar, this imaginary quasar, now we're going in very in a smaller scale, and you will see soon the red material twirling around the central axis, in which represents the dusty toroidal obscuration structure, and the orange part is the accretion disk, and the black here in the center is the black hole. So what's noticeable here is that compared to the host galaxy size scale, which is about tens of thousands of parsecs wide, the size of the accretion disk is only about hundreds of parsecs. So the size difference is significant. So it's very difficult to imagine how this very small structure in this giant galaxy can influence its host galaxy to the point where it can actually change the star formation rate and the color and so on. Then one could think about that, okay, since we're dealing with a supermassive black hole with the 10 to the 9 solar masses, maybe the black hole might have a strong gravitational pull to be able to have a gravitational influence its host galaxy. However, when you do the back of the envelope calculation, then you'll be able to soon find that this gravitational influence is only up to about hundreds of parsecs. So it's not possible to efficiently gravitationally disrupt the 10 to 12 parsec size scale. So that's one of the big questions that we have about feedback. And I think I mentioned feedback about, like, I don't know, already about hundreds of times, and you probably have already heard feedback from the talk given by Megan Donning a couple weeks ago, and you probably heard feedback from Julie as well. Yes.
Could you just like expand on the video, the buildup of gas close to the I guess the structure radius of the black hole, like the cross again, like both that you see in this the cross section.
Oh,
yeah, which it's like a weird dynamic effect, or
like right next to the black hole.
yeah.
Yeah.
Yeah,
there's.
What explains this shape?
well, I hope I know, but I'm not an expert in the smaller accretion size. It's probably better asking someone with the theoretical background or with X-ray astronomy background, because most of my objects I don't really study too much of the accretion disk. I care more about what's happening on top of the accretion disk, and actually later I will tell you more about the fact that although most people think the action is happening in the accretion disk, it's actually happening elsewhere. But yes, I don't think I have the answer to this question. Yes, so moving on to feedback. So I'm also going to talk about something that I'm not familiar with, which I'm going to direct you all to Julie. So in the feedback, there are two different major modes of feedback that we think. So one is the quasar mode feedback, and the other one is the radio mode feedback. So they both effectively work similar way, and they both, as in they would create the same result more or less by disrupting the host galaxy and preventing them from forming stars. But one big difference is that the conditions are different for those different modes to activate. So for example, the quasar mode feedback only occurs when there's a high accretion rate for the high accretion rate objects, whereas radio mode feedback dominates more in the low accretion rate regime. So here in the plot on the left, in the y-axis is showing a different models for different accretion rates. So it's maybe difficult to see, but the very top, this is the model when you have a very, very low accretion rates. And you can see the puffy red spheres represent very, very hot gas that's probably emitting in the X-ray. And the red arrow represents the radio jets. So you see the radio jet is very prominent, and you also have this very hot gas around it. But as we go more to the bottom with the higher accretion rate, you see we no longer see the red structure, and also the radio jet disappears. Instead, we see this blue lines emerging from the accretion disk here denoted in green. So, and we see that the mode changes as a function of accretion rate. So how do these different modes influence, how they influence the host galaxy? So this is a very simplified cartoon showing how the quasar mode, the quasar winds influences host galaxy, how the radio mode, the radio jets influences host galaxy. So what's generally considered what we believe is happening is for the quasar mode feedback, when the outflows driven by the agent radiations is being launched from the near smaller scale in the accretion disk size scale, it is believed that these winds actually interact with the surrounding ISM and directly impacting the host galaxy ISM by injecting energy or by actually removing the full gas reservoir so that the galaxies cannot form stars because there's no fuel. Whereas for the radio mode feedback, it's slightly different. The jets would pierce through the surrounding medium and actually have a different impact on the galaxy ISM, but it still heats up the gas so that it prevents the gas from cooling and forming stars. And we have experts in front of me. If you have any more questions on the radio mode feedback, I would refer you to Julie for that information. So I'm going to talk about the quasar mode feedback and the AGN winds or quasar winds. So to study quasar winds, I'm mostly looking at the broad torsion line quasars, and they're undisputably shows the clearest evidence for energetic winds. And this energetic winds, as quasar outflows, are the way the AGNs feed energy and gas and momentum to the host galaxies. And these broad torsion line quasars are found, or these broad torsion line features are found in about 15 to 40% of the UV quasar spectra, depending on how you select your sample. And based on the absorption features, we find that the outflows typically can have velocities and velocity widths up to tens of thousands of kilometers per second, sometimes reaching more than 10% of the speed of light. And the way these outflows create the torsion line is described here in the cartoon. So you have this gas moving away from the AGN, being expelled from the AGN. And as the gas moves away from the AGN, what observers see is the blue shifted torsion lines relative to the AGN rest frame. So by measuring how much is it blue shifted, we can calculate how fast the gas is traveling, away from the central black hole. And this is an example of a quasar spectrum. So here we have the blue line represents the unabsorbed continuum model, and the black is the data, and the red line here is a preliminary model fit that we have obtained from SimBAL. So basically what this blue line represents is what this quasar would look like if there's no outflow and no absorption. This is how the quasar actually would look unabsorbed. But here we see the significant absorption from various ions from this low-ionized gas, from the highly ionized nitrogen 5, silicon 4, and carbon 4. But we also have some low-ionization ions, such as doubly ionized aluminum. And for some other objects, they also show absorption line from singly ionized iron and singly ionized magnesium. And these outflows are thought to be driven by a powerful electromagnetic radiation from the accretion disk, the powerful energetic photons imparting momentum to the spin-ionized gas. And there are a couple of simulations and models and theoretical interpretation of where these outflows may be originating and how they are accelerated. So so the most popular idea is that these outflows are originating from the accretion disk. And some other people say it's from the torus structure of tens of parsecs away, and some say it's actually formed in situ in host galaxy ISM by the interaction between the hot gas bubble from the central massive black hole and the host galaxy ISM. And you'll notice that you may ask, observational astronomer. Like, why don't we just go measure the look at the outflows and tell the theoreticians what's correct? And one of the reasons why that hasn't been the easiest and why we still have this large range of origin ideas is because it's extremely difficult to measure and constrain the physical properties of this outflow gas, so that outflow gas, and it's also very difficult to measure where this outflow gas is located in those galaxies. Well, so it sounds like you don't know much about BAL quasars, but actually, since its discovery in 1960s, we actually know quite a lot about this system. And mostly because there's just tons of data out there. For example, one of the latest Sloan Digital Sky Survey catalog, they were able to find about 100,000 broad quasar spectra classified and cataloged, and then they're publicly available. And also, other reason why the broad ultralight quasars are very popular targets to study the outflows is because they're very easy to observe. You don't need an IFU or very high sensitive emission line measurements to detect the outflows. All you need is this gas, just all you're along the line of sight. It doesn't have to be that optically thick. And with this large number of data, we're able to people were able to measure perform a lot of statistical analysis, but I put emphasis on the fact that they were mostly focused on studying the empirical parameters that describe this outflow, such as here in this case, this is a composite spectra of broad ultralight quasars cataloged in the SDXS, and here different lines represent different composites made from different broad ultralight quasars with different velocity width, because you can measure the velocity width pretty easily. However, just measuring the velocity with empirical parameters are not enough to actually obtain the physical information about the gas. So that with this empirical information, it's very difficult or nearly impossible to actually pinpoint where this gas is located in the host galaxy. And one of the reasons why it's been very difficult to actually do a proper spectral analysis is because they're simply just very difficult to analyze. So in this figure, I have this the broad ultralight quasar with the absorption lines coming from the iron. And this little trough, only about 100 angstrom wide, it seems like there may not be many lines there, and it may look like it may not be a difficult problem. But once we actually look into the atomic data and actually try to look at what the iron absorption lines are there in that tiny trough, one would find that actually that very narrow trough, at least in this figure, is only spanning about 80 angstroms or 100 angstroms. There are just this large number of transitions occurring in this trough. And they're all blended because the line separation is only about 10 or less kilometers per second. And the intrinsic line width is about hundreds or thousands of pounds per second. So it's very difficult to actually deblend these absorption lines and properly measure the strength of these transitions. And let's say you somehow manage to do that. You still need to perform a careful polarization analysis to convert those numbers to something physical in order to calculate how much gas is, how the state of the ionization state or the gas density. So far, there's only a very small number of broad absorption lines with the well-constrained outflow properties and well-constrained locations and energetics. And I'm not just making that up to make my work much more exciting, but there's actually evidence we found is that this very famous paper in the quasar community, theory et al. 2017, they did the phenomenal work of compiling all the possible agent winds out in the literature with the well-constrained properties. And they were able to find about 100 data points in the various different types of winds. And you can see the BAL winds only take up about 7 data points, even though the fact that the large survey had found BAL quasars in much larger number than any of these either signatures. So we wanted to actually make this different. We wanted to populate this map with much more data from the broad ultralight winds, so that we can get actually more thorough understanding of what's happening with the quasar winds, understand different modes of winds. So the y-axis here I forgot to mention, the log KE, the kinetic energy, measures how much energy is being transported by these outflows. And the x-axis is the volumetric luminosity. It's basically measured the radiation power of the quasar, or how bright it is. So to solve this problem, we decided to flip the table and perform the photoionization analysis first and perform a forward modeling to analyze the spectra. So what we did is we first start with the large number of cloud equalization simulations so that we can get the information about the gas conditions for a wide range of different physical properties, such as ionization condition, and written here is ionization parameter, and wide range of density, and so forth. And combining this information with the other auxiliary information, such as atomic data, and also including the kinetic parameters, such as how fast the outflow is traveling, how wide the velocity width is. Combined with this information, we can actually create a synthetic spectrum, and we perform an MCM sampling to get the best obtain posterior probability distribution and get the best fitting parameters and uncertainties. So with this tool, we need to we're looking at the broad social line quasar examples and we're trying to find what would be the best objects to analyze. So we decided to study the iron low energy broad social line quasars, low quasars. Here also an example spectra shown here, and they're known to have more than thousands of iron 2 absorption lines in their best PD spectra. So these are all blended iron 2 absorption lines here and here. And this large number, and this is coming from to the fact that the iron ions have a large number of low excitation energy levels that can be easily excited with the various different critical density. So once we can actually harness information about this large number of iron absorption lines, we can get a very accurate measurement of the density of the outflow gas, which is critical information that you need to have in order to actually locate where the gas is in the host galaxy. And furthermore, the presence of an iron, simply ionized ion in the gas cloud indicates that the outflow gas needs to be a very high column density because iron is easily ionized. So if you have a shallow gas, you will not have enough iron to create observable opacity. So high column density translates to more material in the outflow and more energetic outflow. And also the low quasar itself is quite interesting in the idea of the picture of a quasar evolution. So this is the one theory that the merger, the various events occur, and that's how the starburst happens and the quasar events happen, and then it becomes a real time galaxy. This is one of the ideas. But low quasars are thought to be in this very particular exciting phase in the middle of the red quasar phase, where it's actively, or it's also called the blowout phase, where a dusty quasar is actively expelling gas and dust to become blue quasars. This is further supported by observational evidence that the low quasars are generally more highly found in the red quasar sample. So now we have selected our targets, low quasars, and we have the tool SimBAL. So we decided to approach this question in two ways. So first, we decided to look at the extreme case, and extreme case to also test our software and to see how it performs. And the second idea that we decided on doing is once we have successfully completed the first analysis using just a single object with the extreme outflow, once it's successfully done, we're going to move on to the large sample of quasars to perform the first systematic study of a large sample and obtain information about what the trends of different properties are and the correlations, and also get the general distribution of physical properties of the outflow gas. So this is the first object that we decided to analyze. So we did not discover this object. This object was originally already cataloged and classified about more than 10 years ago. However, it was actually identified with the wrong redshift. So people couldn't really measure the outflow velocity or where these absorption lines are located. So it was kind of left untouched for a while. So and then we followed this object because it has such a magnificent absorption feature that we wanted to tackle with our software. We followed up with the Gemini and APO near-infrared observations to obtain the better the redshift constraints and also obtain the various information about the emission lines. And we were surprised to find that when we applied the correct redshift that we were able to get from this very strong H alpha line, we're able to, even without the detailed analysis, we're able to find that this outflow, this absorption feature is coming from the outflow that's traveling more than 10% of the speed of light. So this is I'm trying to show you how SimBAL perform with this data. So here in the black is the data, and the y-axis is flux, and x-axis is the west wavelength, and this is the zoom in plot showing what's to showing the where the main events happening with where the iron absorption lines occur. And this is our best fit model. So the red is the best fit model, and the blue is again the unabsorbed continuum, what the quasars would look like without this absorption. And here at the bottom, it's showing a bin velocity binned model. So here, what I wanted to show you here is that this white trough is not just made up of line blending. Well, line blending also occurs, but it's actually made up of not only just the thousands of absorption lines coming from the iron to the transitions, but also it actually has a wide velocity width of spanning more than about 10,000 kilometers per second. And we're able to measure the density and the ionization condition of this outflow gas, and we're able to constrain with high confidence the mass outflow rate about 3,000 solar masses per year, and the outflow energy of about 10 to the 48.1 ergs per second, which was quite a surprise to us because this is actually more than the same strength as the radiation power of the quasars. And from this, our model, we are also able to constrain the geometry of the outflow, and we're able to constrain that this outflow, the FU-Loba outflow gas, is likely located about tens of parsecs away from the central engine, and it's probably that the gas is actually originated from the torus, not actually from the accretion disk. And to give you a brief summary of what we found in the 1352, the first, we were able to prove that our SimBAL performs superbly in constraining the various different physical properties from this very highly complicated absorption spectrum. And from the science point of view, we're able to discover this most powerful BAL quasar alpha ever found. And we also find evidence that this actually is not an accretion disk outflow, but it's actually a torus wind. And if you're interested in more about what we talked about in this project, you can also take a look at the Gemini press release that we did in 2020. And because this object is such an extreme and such an exciting object, which is powerful outflow, this could be potentially an interesting target to follow up the JWST or HST to study either the host galaxy property, because that's just such an energetic event is happening. So the host galaxy could be disturbed, or it could be going through a merger, or some other events could be happening. And JWST and HST, they can provide information about that as well. And the next, we move on to studying the large sample of FU-Loba quasars. So this marks the first attempt in studying the large sample with the proper spectral analysis. And here the plot is the one that I showed. It's an identical plot from February 2017. And as you can see, this is pretty empty with only a small number of absorption line outflows. And from our sample, we're able to add a large number of data points to this plot, and also find the interesting trend between the FU-Lobas and where they sit, how they compare with the other form of quasar winds. And I'm going to briefly show you some of the spectra that was included in the sample. So we had, so in this 50 object sample, we had a wide variety of spectral morphologies, starting with some of the objects that have only a moderate amount of absorption. So again, the black is the data and the red is the model. And we have a wide range of objects, the ones that have very small absorption features with the low outflow velocity and low velocity width, to some more moderate absorption. And we also have in our sample the extreme outflow objects that look similar to the objects that I showed before. So in this entire bandpass spanning from 2,000 to nearly 2,800,000 angstrom, there's just a lot going on here. There are thousands of absorption lines are creating this absorption trough, and also velocity width is also very significant, nearly about 10,000 kilometers per second. So it's all blended. But with SimBAL, we're able to accurately model this object and get the quite nice constraints on the various physical properties. And the object at the bottom looks sort of similar in the sense that they also have this wide trough, but this object I've put it on the slide to demonstrate what I call a loitering BAL looks like. So this is a new type of broad absorption line outflow that I was able to identify in our sample. And I'll describe a little bit more in later slides why they're so important and why they're exciting and why they may not even be an outflow after all. So from the best fit models, we're able to constrain the parameter various physical parameters and also measure how far these outflow gases are located from the central supermassive black hole. So here the y-axis here is written in log r and log parsec. This y-axis represents how far this outflow, FE-level outflow gas is from the central black hole. And the x-axis is log v, which is the ionization parameter that describes the ionization condition of the outflow gas, and the log n is the gas density. And before we started the analysis, we wanted to see what this distance means. Does that mean, do they actually reflect the origin of this outflow gas? So we calculated the dissipation time scale and also travel time scale, and we were able to find that the dissipation time scale is significantly smaller than the travel time scale. Unless there is a really strong confinement mechanism, what we can say is that this outflow gas has barely moved since its creation. And based on the assumption that what that means is that the locations that we found from our work basically reflects the origin of this outflow clouds. And one of the first things that I point out, I normally emphasize this point when I'm giving a talk in the quasar wind community, especially when there's like theoreticians, because most theoreticians prefer this wind model because, as I mentioned, these are radiatively driven winds. So they need energetic photons to push this gas to higher velocity, and those energetic photons are coming from the accretion disk. So in their models, generally, their winds are generally ejected from the accretion disk. However, from our sample, the most compact, the most nearby outflow is still about a parsec away from the central black hole. And that means we do not find any evidence supporting, or we do not find any evidence for this wind in our FE-level sample. So other thing that I like to note is that one of the interesting discovery is that, as you can see, the locations of these outflows span more than 4 orders of magnitude. So these energetic FE-level outflows are located all throughout the different size scales of host galaxies, which could potentially suggest that they may actually be interacting with the host galaxy IXM rather than just being this powerful outflow just confined within the quasar size scale, the AGN size scale. And for these nearby outflows located about parsec to hundreds of parsec away, we believe most of these outflow gas are originating from a torus or a polar dust structure, or some from the narrow line region clouds. And we believe, based on the properties and comparing that with the theoretical predictions, we believe these outflows are largely accelerated with the radiated line driving, or in some cases, dust acceleration. And for the gas that's more further away, we believe this outflow gas has not actually originated from the AGN itself. Rather, they're formed in situ in host galaxy IXM. Although they're still considered the quasar winds, because the way it works is that there's this idea called the cloud crushing idea, where the hot gas bubble comes from the AGN. And as it meets the cold ISM out in the host galaxy, then it creates more clumpy structure to create the FE-level outflow. So basically, these outflows are powered by the AGN, although the mass, the gas is actually not necessarily from the AGN itself. And with the various parameters that we have, we perform the various correlations to see if what we find in observation matches the theoretical predictions. So again, the y-axis, we have the radius, or we call it radius, but this is essentially what it means is how far the gas is from the central engine, central supermassive black hole. And the x-axis is the velocity offset, or the speed of these outflows. And here we find this nice correlation that the powerful and faster outflows are located more compact, and the slower outflows are on the kiloparsec scale, which is expected for the radiatively driven winds. Then if my story ended here, that could be nice and simple. However, I'm not showing all the data points, and actually we found there's actually a large number of outflows that did not necessarily follow this trend, and they seem to show this particular behavior where they're located fairly close to the central engine, only about a parsec away, or parsecs away, but they don't really have an extra powerful kinetic movement. And so we coined the term loitering outflows. So we started calling them loitering outflows. And upon a further understanding of the quasar properties by looking at their accretion rate and the black hole mass, we were able to find that actually these loitering outflows are all found in quasars with a low accretion rate. So this seems to suggest that these loitering outflows in terms of the wind phenomenon, they actually have a different formation or acceleration mechanisms than this regular typical outflows that we expect from the envelope quasars. And this is a plot that I showed earlier, but now it's color-coded with velocity. So we find that objects with a higher luminosity, more brighter objects, have more mass, more powerful and faster outflows, which is expected for the radially driven winds. And another information that we're able to find is that when we measure the reddening of these objects, so the color axis here represents if it's close up to 0, negative means they're blue, and the higher the number means that the object is brighter. So this means that the environment that this quasar is in, or the quasar itself, could be dusty, or more specifically, there could be just a dust along the line of sight. And we find that the more redder BALs, the quasars are, the faster the outflows that we're able to find in these objects. And this could mean two things. One could say, so maybe the dust itself, the dust is actually connected to the outflow. So maybe the more dusty the outflow, more reddened, maybe that means they're actually helping the outflow, helping the gas with the rate of driving by contributing their opacity. The other idea is that maybe they're not necessarily directly related to the outflow themselves, maybe they're more related to the property of the quasars. As I mentioned earlier, the red quasar tend to show more outflow activities, and that's exactly what we find, that the red quasars seem to have more active outflow activity going on than the blue quasars. And that's currently a very interesting topic that's been discussed in the quasar community. And some people say that the red quasars actually have completely different radio properties, and they may actually have a different revolutionary track than the blue quasars. And we decided to go further with our project. So not only we looked at the absorption line features to study the outflows for properties, we also took a look at the optical emission lines for subsample objects with the low redshift, where we can actually get the information of the BAL lines and oxygen-free lines in the red end of the SDSS spectrum. And we were able to measure the black hole mass and the Eddington ratio, or the accretion property. And surprisingly, we're able to find that our sample actually split into two groups, the high accretion rate objects and low accretion rate objects, and not much in between. And these two groups also show the very distinct outflow properties. So for the high accretion rate objects, they have this correlation where the more compact objects have a higher velocity, more distant outflows have a lower velocity. And that wasn't the case for the low accretion rate objects. So this also goes along with what I mentioned about the loitering outflows, and this further seems to suggest that the outflow properties and the way the outflow are accelerated and generated are very highly dependent on the accretion state of the central supermassive black hole. So to summarize what we were able to find from the samples, at first we're able to securely, confidently measure the location of the outflow gas, and they surprisingly span more than 4 orders of magnitude, some the parsec scale very compact wind to a kiloparsec scale wind that the gas is actually located in the host galaxy. And these different size scales may indicate these outflows may actually have different origins and different geometry, which I didn't go into details today, and maybe they also have different physical mechanisms behind their acceleration and acceleration mechanism. And these loitering BALs, I was able to find this group of bizarre outflows, bizarre FLOs from our sample, and they seem to have very different wind properties and also have a very different central supermassive black hole properties. And they may actually be giving us a hint about what we can expect to happen when we change the accretion rate of the supermassive black hole. Maybe the winds don't just suddenly disappear. Maybe the winds turn to something else that we're not familiar with yet. And compared with the quasar properties, we find that FLOB quasars are more luminous and more red, have more faster energetic outflows. And when we combine the information obtained from the optical emission line analysis, we're able to find that they're actually divided into 2 populations. So now we have this wealth of information, and this is just a highlight of what we were able to find in the project. There are the other information that we're able to gather. So we're very excited to get all this information ready, and then so we decided to go further with this project. So I'm looking at the higher redshift objects. So here on the plot, y-axis is the luminosity of the quasars, and the x-axis is the redshift. And the blue dots represent the low redshift objects, and the red dots represents the high redshift objects that we're currently working on. And the high redshift objects are particularly of interest, especially in the context of galaxy or quasar feedback, because at the redshift of 2 in this region is where the quasar feedback activity in the star formation was much more going on much more actively than the low redshift. So this period is also called cosmic noon. It's a very critical period in understanding how the feedback works. And for this flux limited survey, by looking at the higher redshift objects, we are going to also be able to look at how the outflow properties change with the luminosity and the black hole masses. And we have some preliminary results from this project. So this is the plot that I showed earlier. Now it's with all the data points from the low redshift sample. And we're able to find and add extra data points from the higher redshift objects. They have higher luminosity, and as expected from the low luminosity sample, the trend seems to continue that the higher luminosity objects have this also more energetic and faster outflows. And in order to do that, in order to expand your sample, you first need to find them. You need first to find the FA-low quasars. And they're not that common. There are only about 2% of quasars that have FA-low features. And oftentimes, they're not actually properly cataloged as quasars in longitude star survey or other catalogs, mainly because, as I showed you before, sometimes when the absorption is so severe, they no longer even look like quasars. So the classification mechanisms often or sometimes misclassify them as non-quasar objects. So for instance, the first object I showed you with the most strong BAL outflower detected, it was first discovered as a quasar, but later, after once they changed the classification mechanism, it actually stopped appearing in the quasar catalog. And so our group developed this convolutional neural network called an FA-LowNet. And so far, we were able to find over 400 FA-low quasars from the STX SDR14. And this number may look small, but this is a significant improvement than before we invented FA-LowNet, because more than half of the FA-low quasars that we were able to find were actually unique FA-low detections that were not known before. And the FA-LowNet is basically a convolutional neural network to classify the FA-low quasars. And in order to train this convolutional neural network, we had to get a large number of data, but that was not possible because there's only about 150 previously classified FA-low quasar spectra out there available. So we had to think about how we can actually augment the training set. So we decided to use SimBAL, although SimBAL is meant to perform spectral analysis, but since this is for modeling spectral synthesis code, we can actually create the absorption profile as a function of various different outflow parameters. So what we did is that we collected the non-BAL spectra from the catalog, and we multiplied them with our absorption profile generated from SimBAL, and then we created a large number of synthetic spectrum to train our neural network. And it's been working really well, and we'll have a couple more updates that we're intending to do. And we hope to publish the catalog and also FA-LowNet soon in the future. And currently, we're only looking at the quasar catalog, but we're also interested in seeing what we can find from the galaxy catalog or star catalog, because some of the FA-low catalog misclassified as a galaxy objects or stars. And this is not just for our project, but SimBAL group and I are part of the 4-meter multi-object spectrum telescope survey. So this is the upcoming ESO survey campaign. They'll start the operation in 2024 with the plan of observing more than 20 million spectra in the next 5 years after the start of observing. And we are part of specifically with the S6 quasar AGN survey, and we'll be using FA-LowNet to find the FA-low quasars in the southern hemisphere. And there's other project that could be interesting that we are interested in doing, that I'm interested in doing, is to incorporate machine learning techniques to SimBAL to make it more efficient. So currently, the SimBAL, although it works really well, and I was able to analyze 50 objects in the span of 3 to 5 years to figure out my PhD. But that's not really really efficient if you have a large number of objects and with upcoming surveys going on. So the bottleneck is that as with any other spectral analysis code work, it starts with the initial fitting. So there's human input and we evaluate the model and so forth. So if we can use some machine learning techniques to at least find some priors to help us start the fitting process, it could significantly help us with the speed. And also we're also experimenting with using different computer languages. Currently, SimBAL is entirely written in Python, and some experiments that we did using a different language, we found that C, if we change the engine just some parts into C, that then our computation speed will actually double, if not more than that. So that's one of the plans that we have in our collaboration. And the other idea that we're thinking is that, so the FE-LONET is a spectra classifier. It classifies the FE-LONET spectra using the spectra. But that means you actually need to already have spectrum data from the survey. But what if you only have photometry data over the SCD? So here, these are the SCD data points. Here with SDSS, and this is 2mass and Ys. So what if you only have this information? Would you still be able to detect these extreme objects? So that's one of the interesting projects that I'm interested in following in the future. And I think I'm almost running out of time, so I'm going to just put the summary slide on top. But most importantly, I also want to acknowledge all those who helped me achieve all these interesting, exciting projects throughout my PhD, and also I also, of course, need to acknowledge my funding sources, and I'll conclude my talk by just putting up summary slides so that you can see if you have any questions.
Good.
So you said these winds are relatively driven
Yes.
and they're close to the torus.
Somewhat. Yes.
Okay. And so are they line driven? Because you also mentioned dust driving. You know, for stars, you either have dust driving in full stars and then you have line driving in hot stars. So what is the driving?
So so the idea of BAL outflow, or the way back when they're first trying to understand the theoretical background, the idea actually came from the hot star winds. So mainly, even now, it's, if I have to choose between the two, if I'm, I don't know, writing an exam, I'll probably just say a line driving. So that's clear evidence. We have the line locking, we have such a gazillion spectral features that suggests it's line driving. However, one of the reasons why we say that the dust could be contributing to the driving of the outflow is that when we are measuring this parameter called force multiplier, where we are looking at all the opacity present in the gas and just some sort of basic, almost like a back of the envelope calculations of how fast the very thick outflow, such as FE-LONET outflow, they have Coulomb density of about 10 to 23rd. So in order for those very, very thick gas to accelerate to such high speed, like tens of thousands of kilometers per second, the calculation with the force multiplier and the basic line driving was not sufficient. However, we still need to go, we still need more thorough understanding of how dust driving occurs, because in this photoionized gas, once you start adding dust, the photoionization balance changes completely and it becomes very difficult to populate the highly ionized species. So that's something that we're interested in looking in the future. And there's some ideas where they say that the dust was actually present and they actually push the gas out, but they somehow decoupled. And we're seeing the decoupled portion where it's just the gas. So
Are you sure there's no iron 3, iron 4, iron 5?
So for the highly ionized, so that's actually a very exciting question, and the question that I'm kind of scared to answer, because we have some objects that seem to show extremely strong iron 3 and iron 3 without iron 2. So that poses a lot of interesting questions, and that's one of the things, the kind of mini project I want to work on, because I found some of the objects that seem to show nothing but iron 3. And some people suggest like you need a very specifically extreme gas condition to create a situation where you only have iron 3 but not iron 2.
Oh, in stars you have iron 4, 5,
Yes,
6.
but I think with the quasar SCD, we don't really find them that much in the recipe. But in that case, but we also found that one of the controversial idea in the BAL quasar, maybe not controversial, maybe I'm the only one thinking controversial idea, is that some people say there's like a shielding gas that protects the gas from over ionizing. And that's one of the scenarios that I'm thinking of applying for the iron-3 model, because when I did some polarization simulations, some of the cases actually did help me produce a significant amount of iron-3. But to going back to your original questions, it's mostly iron-2, and that was the original definition for classifying FE low-BALs. But some objects do show iron-3 around 19.
So just before your first summary slide, I think you showed the different paths that a ray could take to get to the observer. And I wonder, how much do your results depend on your model of what the torus disk look like, or what angle it is relative to you, and all these different like morphology configurations.
Yes, so you're talking about the cartoon picture that I showed for the J1352, where we have the torus and we have the accretion disk, and there's some light goes to a different direction and it bounces back to the observer. So, so that's a very specific case. We're able to get a very tight constraint, or should I say more specific geometrical information from the objects, because I didn't go in detail, but the object actually showed more than just the broad ocean line features. It actually had very strong evidence for scattered light, and also had an extra component where it seems to have very different polarization conditions. So in that specific case, we were able to get a lot of information about geometry and create the cartoon, but
So are you sensitive to how inclined the disk is relative? So there are two different main school of thoughts in BAL quasars. One is that one idea is that it's very directional. You need to really see almost at the very low angle or high angle to the accretion disk in order to see this outflows. And you don't see it if you see it face on. That's one idea. But the other idea is that you don't really need that, and you can see the broad occlusion line from any sight line and any angle. So to answer your question, does it depend on the viewing angle? It may not. So I think, I mean, it's a recording, so I cannot say something that's in discussion. So we're somehow surprised and excited to find that some of the FE-low-BAL outflows, FE-low-BAL objects tend to have broader H alpha emission, which seems to suggest we're looking at more edge on and seeing more of the inner parts of the accretion disk, of the broad emission line. So that seemed to suggest that FE-low-BALs it's worth viewing as edge on, but I would say the result is inconclusive, and we still think it could be directional. Maybe we need to see these objects in a specific angle, or maybe they just appear only 20% in the quasar lifetime.
Other questions? I'll ask a fun one. So I'm wondering in your spectra, when you fit the spectra,
Yes.
do you include the possibility that there might be two black holes, that it's a binary system? Because there's like this whole mystery that we're not finding binary supermassive black holes as models predict.
Well, I would need to first take a step back and think about what spectral features I would expect if it's a binary. So I know there's some group the filter somewhere where they're trying to find the spectral signature for the binaries by looking at the emission lines. And for absorption lines, I mean, we do simultaneously model the emission lines as well, but we don't normally consider them having like a binary feature or anything, just a typical quasar spectrum on PCA to get the bit templates. So answer is no, we don't really think much about the binary situation. Although, but that's a very interesting thing to think about.
Yeah.
Perhaps that's how we operate.
Yeah. All right. So thank you so much.